Hi Year 12 and welcome to our first lesson for the topic of differential equations. In this topic we're going to look at differential equations, slope fields, techniques for solving differential equations and applications. A differential equation contains a derivative. That's it. So it could be as simple as dy dx is equal to 0. An ordinary differential equation, which we abbreviate to ODE, is an equation that expresses any relationship between an unknown function, which is often y, its independent variable, which is x, and one or more of its derivatives, like dy dx. Now, not all of those things are compulsory. The derivative is, but we don't have to have the independent variable involved, and we don't have to have the unknown function involved. So here are some examples of ODEs. We have dy dx equals 2x, d squared y dx squared equals y. And this one's got two derivatives in it. D squared x dt squared plus 2 dx dt is equal to 2t. The order of an ODE refers to the highest order derivative that appears in the equation. So here we have a first order differential equation, and these two are second order differential equations. Now in this particular course we're only going to cover first order ODEs. The solution to a differential equation is the function that satisfies it. We've been doing this for a while. So if we want to solve dy dx is equal to 2x, what we do is take integrals of both sides with respect to x. The left-hand side becomes y, and the right-hand side is the integral of 2x dx, which is x squared plus c. So here's an example. Show that y is equal to the square root of x squared plus 1 is a solution to dy dx is equal to x over y. Now what we're going to do here is differentiate this and then try and get this expression x over y. So let's start here. Y is equal to x squared plus 1 to the power of a half. Differentiating, we get dy dx is equal to a half x squared plus 1 to the power of negative a half multiplied by the derivative of this, which is 2x. Tidying this up, we can cancel these 2's, and I'm going to drop this x squared plus 1 to the power of negative a half down to the denominator. So we have x over the square root of x squared plus 1. We're nearly there because this is equal to y. So it equals x over y. And so we've proved it. An initial value problem, also called an IVP, combines the differential equation with initial conditions so that the constant can be resolved. Now previously in advanced, we've just called this resolving the constant. This is a little bit more technical language, so initial value problem or boundary value problem it's also called. For example, solve dx dt equals 3t squared plus 2t given x equals 3 when t is equal to 0. So we're going to integrate both sides. X will equal t cubed plus t squared plus c. Substituting in our initial conditions, so x is 3, when t is 0, c is equal to 3. Therefore, x is equal to t cubed plus t squared plus 3. Now, first order differential equations take many forms. Here we have a differential equation in terms of the independent variable, but we could have it in terms of the dependent variable or both variables. Now, when our differential equation is given in terms of the independent variable, we just use our normal integration methods to find the solution. We're just going to do the integral of both sides with respect to x. So y will equal x cubed over 3 plus c. And of course, we learnt that this gives us a family of solutions because we don't know what the constant is. Okay, that's it for this lesson. Our next lesson is on slope fields.